Hello and welcome everybody to the course Crystal Engineering. Hello. Today we will talk little bit about intermolecular interaction. We will show how important these weak bonds are in crystal packing and how we can use intermolecular interaction to design desired structures. First, why do we study crystal engineering? The reason is you cannot explain each properties of compounds by their molecular structure. Several properties like stability, melting point, bioavailability, solubility are attributed to the crystal structure or not to the molecular structure. The reason is the internal periodic structure. This is the crystal structure. This is responsible for several properties. Well, and in the case of crystal engineering, I would say we have three main topics, chapters, which are interesting. First, we must analyze crystal structures, try to understand the crystal packing, what are the driving forces, and then use this understanding, this result from the analysis for crystallization experiments. This is what we want. Well, let's start. Everything starts with a molecule. This is a classical chemistry. As I said, not all properties are explainable by the molecular structure. This is the first thing. And the second thing, if we look in biological systems, well, what do you see? You will not see the breaking, the making, the formation of chemical bonds. What you see is mostly the formation of loose aggregates, DNA helices, or drug design. Most important feature for these compounds are non-covalent intermolecular interaction. Showing here, this is DNA, you know by yourself from the chemistry. Responsible are with hydrogen bonds. Or another point, if you look, for example, to drug design, for example, you see it here, dorzolamid. This is a drug against glaucoma. Yes, glaucoma, this is in German, the name is grüner Star. And the problem is the inhibition of water outflow from the A chamber. Yes, and the aim was or is to find a molecule with a perfect size to fit the bonding pockets and inhibit the enzyme, a special enzyme. Yes. Well, and if you look here, this is dorzolamid, and you have a look here. The importance, once again, are the intermolecular interactions here of the dorzolamid, with here the pocket, and you see it here, some residues of an amino acid. So, the intermolecular interaction, these are the most important driving force in biological systems. This is one thing. Next thing, have a look. Intermolecular interaction. Intermolecular interaction are not restricted on solids. You will find it in liquid also. In both liquids and solids, you will see that the molecules are aggregated by intermolecular interaction. Have a look here, water. You know, hydrogen bond, water. Hydrogen bond between water molecules. Okay. Hydrogen bond in ice. You see it here. And if you look here, this is melting ice and here's water, the molecules. And this is the typical structure, I would say, ice sketch of a situation in liquid. You see very nicely, here's the water molecule, you see very nicely here the hydrogen bonds, and exactly in the same manner like in the solid state here. But in this case, you have ordered structures. You can very nicely see it here. Oops, here. As I have shown you last time, this program, visualization program, this is one form of ice. Switch here to capped sticks, one form of ice, two molecules. This is the asymmetric unit, and when by using all the symmetry, here are the hydrogen bond, intermolecular interactions, very nicely you see. You can here expand. You see here, have a look, we can measure the distance. Measure the distance, for example, here and here, 1.83. If you look to a packing, you see it here. It's a little bit confusing, but so we avoid the cell exit and we avoid all these hanging contacts. Very nice to see it here, the structure. This is a crystal packing of ice. Ordered structure and driving forces. I see here the ring system, 1, 2, 3, 4, 5. Ring systems here, the holes, cages. Well, okay, going back. With this, in both systems, you have intermolecular interaction. The difference is ordered and non-ordered. Next thing. See it here. And the hydrogen bonds are not only restricted to DNA and some special things like water. Hydrogen bonds is very often found in organic structure. You see it here, the phosphonic acid. And what you see is layer structure. One thing is here a layer formed by hydrogen bond, and then here additionally you see here the phenyl groups are staggered, ordered. So. Well, okay. You have with strong intermolecular interactions like in water, this is one thing. Directional interaction, we will coming back to this point, directional interaction. And then on the other side, I would say, of interesting intermolecular interaction are always van der Waals forces, which are closely related to close packing. Yeah, you know from a study from the first semester, square and hexagonal lattice, and this phenomena of ordering of atoms and molecules. You see it is only not so strict to atoms, it's also molecules. There are no strong interaction, and you will find it, for example, in alkanes, or here's 1-phenylidecane. Have a look. 1-phenylidecane here. This is staggered. There's no strong intermolecular interaction here. What you see is always here this one chain is exactly in the whole of the other chain here formed, or something like a staggered formation. Okay. And third group, very interesting, I would say very interesting, intermolecular interaction are PP interaction. We can decide between two different points of PP intermolecular interaction. Yes, one of them is face-to-face and the other is edge to face, so T-shape. You see it here, A is face to face, and see here it's a little bit shifted. It's not exactly stacked. You see it's a little bit shifted. The reason is that you have different partial charge in the system here. Positive partial charge on the hydrogen atoms and negative charge on the ring. This leads to this little bit shifted face-to-face orientation. The second point is here edge to face. The edge to face, in this case, or you can also say T-shape. CH group are points to the negatively charged ring, so this leads to this very nicely system. You see very nicely, so the distribution of electron density, which is responsible for the situation for these two different types, and you will find both types in molecular structure and also in benzene. One is benzene 1 atmosphere, ambient temperature. See it here, T-shape. And if you look to the crystal packing at high pressure, see it here, we have a face-to-face. Have a look. Benzene ambient, here, nice. And we can tap. So I avoid the hydrogen atoms here, so maybe you can see a little bit better. Maybe, oops, packing, we maybe reduce here. Yeah, I see it better here, no? And on the other side at pressure, looks like here. So, two different types, T-shape and face-to-face. Well, this is one point. The next point is we can use, this is very nicely, well, this is a very fine example to learn something about crystal engineering. I said first, crystal engineering, the first step is analysis of crystal structure. What do we learn? We learn the distribution of electron density in benzene molecule is responsible for the two different types. And we can control the crystal packing by, I don't know, pressure, temperature, and so on. And always we have different partial charge in the system, and we can use this different partial charge for the crystal packing. Okay. Can we use this? We can use this. And let me show here. So this is the first example about using crystal engineering. We're using crystal structure analysis to design a special crystal structure. Well, what do we have? We have the crystal structure of benzene, exactly what he said. Here we have two different partial charge, minus of a ring and positively charged the hydrogen atoms, CH atoms, okay, with system here. And if you look to hexafluorobenzene hexafluorobenzene. What is the situation hexafluorobenzene? Fluorine atoms are highly electronegative and they withdraw the electrons from the ring. So, and the result is, this is exactly a reversed quadrupole moment to benzene. Yes? So, in this case, this is positive. Okay. So, can we use it? We can use it. Once again, this is the crystal packing here, crystal structure of benzene. And this is a figure of a crystal structure of hexafluorobenzene. You see it here. What happens if we mix both compounds together, like a cocktail, in a solid state? The result is here. What we have now is face-to-face systems. Yeah? Here, very nicely, look here, benzene, hexafluorobenzene, benzene, hexafluorobenzene. Wonderful. And you see it here, the layered structure, very nice. This is called co-crystal of two compounds. In this case, benzene, hexafluorobenzene. Have a look. Here. Where is it? Where is it? Where is it? Where? Here. Huh? Huh? With hydrogen atoms. Very nicely you see here face-to-face orientation of a system. Packing. This is the structure. First example, how you can use the results of crystal structure analysis to design your own crystal structures. Okay? Fine, huh? Good. So, we directly introduce the new chapter called co-crystal. Co-crystal, what is it? You can look once again in the internet and you can look in the literature and you will find a huge number of different definitions. Co-crystals. In the context of this lecture series, I would say co-crystal is a structurally homogeneous crystalline material that contains two or more neutral molecules, not ionic species, very important, two or more neutral molecules that are present in definite stoichiometric amount. For example, it's 1 to 1, 1 to 2. Okay? And co-crystals are very interesting in crystal engineering scene. We will see it a little bit later in pharmaceutical industry, for example, material science, and so on and so on. For example, this is here a contribution in crystal ground design about co-crystal. Have a look here what is going on. This is here the compound, yes, and they thought about or they investigated which molecules are suitable to build up co-crystals. And what they said is, well, have a look here on our compound. You see a functional group, yeah, CO double bond, NH, CO double bond, and they selected special compounds called co-former, which includes or exhibited here nitrogen atoms or keto functions or some other functional groups, and look if it's possible to build up such units which are responsible to build up co-crystals. Okay? So, this was was the first examples of co-crystal design, first example of crystal engineering. Once again, you look to crystal structure, analyze the crystal structure, think about driving forces, extract this information and use this information to build up your own crystal structure. On the other side, don't forget, crystal engineering is always based on a molecular concept. And molecules, you know it from organic chemistry, are held together by a strong interaction called chemical bonds. And we don't revert spontaneously to atoms, which is very important. And in comparison, molecular crystals, crystal engineering is the science of molecular crystals, you can say. And molecular crystals is a collection of molecules. And this collection of molecules is held together by strong interaction, okay, and associated by weaker interaction. Once again, this is the intermolecular interaction we are talking about. No? Well, let's have a look, compare a little bit more molecules and molecular crystals and have a look on the units. We should look first on bond lengths. These are typical bond lengths of chemical bonds, CH, CC, C double bond, or benzene. Round about 1, 1.5, 1.3, 1.4. And you see it here, OH and NH with a roundabout bond length, roundabout. On the other side, if you look to intermolecular interactions, in this case hydrogen bonds, you see with OH is expand 1.5 to 2.2. In the case of you have a strong with a moderate hydrogen bond. In the case of weak hydrogen bonds, 2 in the range 2 to 3 angstrom. And well, this is really the roundabout. These are only thumb rules, not more. No? You see it here is a very large distance and a large distance here. And well, for example here, intermolecular interaction in water, you know, ice, we have seen 1.97, that's not absolutely correct. You will see it here. It's in this case it is reduced. No? We have one here, 1.85 roundabout, and in liquid also nearly the same. This is the first point, so the distance. What's going on with energy? The bond energy is around about 300 to 500 kilojoule, mostly. Exception, for example, sulfur is 200. Yes. And now have a look on hydrogen bond energy. Now hydrogen bond energy, look here. Only 30, only 20 kilojoule. With a really big difference to the bond energy of a covalent bond. And if you look to very, very weak intermolecular interaction like van der Waals forces, you see an energy only below 10 kilojoule per mole. Question is, what are strong and weak intermolecular interaction? Well, this question is not easy. You will not find an easy answer for this question. On the other one side, you have very strong hydrogen bond. In this case, with anion and 160 kilojoule. And if you compare it with a very, very weak covalent bond, see carbon iodine, only 125. But, well, this is the crystal structure here of this compound. You see, okay, this is with anion, we see it here. and you see it's nearly linear, and you see it's exactly the same. This exactly the same bond length, the distance here from the H to F, and from the second H to the second fluorine. Well, and if you look to the crystal packing here, you see that this unit with this very strong hydrogen bond, well, is isolated, you can say. There's no really significant, interesting intermolecular interaction to the counteranion, the countercation here. And it is very nicely, you can see here that such compounds with such a strong hydrogen bond are not usable in crystal engineering. This is, isolated, dead unit. So the majority of hydrogen bond, mostly of them, are in the range between 4 and 60 kilojoule. Yeah, strong 2080 roundabout, and weak, and we are on the other end 4 to 16. But don't forget, this is important. A lot of interaction which are important in the context of crystal engineering are in this region of very low weak intermolecular interaction, 2 to 20 kilojoule per mole. Design and supramolecular chemistry is a chemistry of intermolecular bonds. This was a sentence expression von Jean-Marie Lilien, Nobel Prize winner, 1969. Supramolecular chemistry is a chemistry of intermolecular bonds. This is a chemistry of these weak intermolecular interactions. And this is a very nicely contribution from Desiraju in Nature, the top scientific journal, the title Chemistry Beyond the Molecule. You see, this is part of the title of a lecture series, and it's very nicely written contribution. And here are three examples of his contribution, very nicely shown. For example, you have here donor exactor with a silver cation. You have here formation of clutrate. This is B clutrate. This clutrate is building by hydrogen bond. Exactly this hydrogen bond we have seen in ice or DNA and so on with drugs. No? And you can use this clutrate as a host for gas, for example, you see it for noble gas. No? Or another thing, here you have a cryptant, and inside is here a metal ion, and you can use this. This is usable applications. You see, ultraviolet light is coming in, and you have a shift of a light wave, and coming out is visible light. No? Very nice examples showing the importance of intermolecular interaction in supramolecular chemistry. At the end of this video, we should announce we have two different classes of interaction. We have an isotropic and the anisotropic interaction. The isotropic interaction we have seen van der Waals forces, close packing. This is a very simple level of molecular recognition. And we have seen, I've shown you examples, anisotropic interaction. This is a higher level of molecular recognition. And the main feature of this anisotropic interaction is directional. Directionality is very important in crystal engineering, looking for intermolecular interaction with a high directionality. So, and I would say, summary, crystal is a supermolecule aggregation, molecular structure, molecular crystal, and in combination for an intermolecular interaction. Okay, these were some basics about crystal engineering, and the importance of intermolecular interactions in crystal engineering.